Modern bulk ore processing operates on a massive scale, moving thousands of tons of rock on heavy conveyor belts every single day. But the actual extraction of the gold happens deep down into the microscopic pores of the rock itself. Across the mineral processing industry, the dominant method for pulling this gold out of ores and concentrates is cyanide leaching. The underlying chemical reaction required to dissolve gold is relatively straightforward in a laboratory. However, replicating that reaction across massive industrial tanks while maintaining high recovery rates creates a highly complex, multivariable optimization problem. To maximize extraction efficiency, process engineers must rigorously control 6 interacting variables: grinding fineness, cyanide dosage, pulp density, leaching time, inflating volume, and the pH and temperature of the slurry. True process optimization requires stepping away from guesswork and building a mental model from the first principles of chemistry, mapping exactly how they dictate the physical constraints of the plant. Failing to balance this matrix directly causes massive reagent loss, blown capital budgets, and severe environmental hazards. We start with a strict chemical rule. Gold is a highly inactive metal. To extract it, we have to force it into a liquid state through a specific complexation reaction. The mechanism relies on unbonded cyanogen, often referred to as Cn-, making direct physical contact with the gold surface. But the cyanogen cannot do this alone. Oxygen must be present in the fluid, acting as a catalyst. Together, they attack the solid surface and drive the complexation forward, which lifts away dissolved gold molecules, known as AuCN2-. This baseline chemical requirement dictates our first operational variable, cyanide dosage. To keep the reaction moving without stalling out, the pulp inside the tanks must maintain a continuous, highly specific concentration of unbonded cyanogen. It also defines our second variable, inflating volume. Since the presence of oxygen directly determines gold solubility, the plant must use mechanical agitation or direct air inflation to constantly force high volumes of oxygen into the pulp. While oxygen and cyanide extract the gold, combining them creates an inherently unstable chemical environment. This forces us to introduce rigid safety boundaries that wrap around the entire operation, specifically temperature, pH, and agitation. The primary threat here is volatilization. The cyanide inside the processing pulp easily reacts to form hydrocyanic acid, or HCN, a highly toxic, lethal gas. This scatterplot maps out the exact environmental controls required to suppress that reaction. By plotting temperature on the y-axis against pH on the x-axis, we can see exactly where the process needs to live. The pulp temperature must be strictly held below 15 degrees Celsius, and the pH must be locked tightly between 10 and 11. To ensure those exact limits remain perfectly stable and evenly distributed, the massive tanks rely on continuous, uniform mechanical agitation. There can be no stagnant zones where acidity spikes or temperature drifts. Establishing these chemical baselines is the non-negotiable first step. Without them, the plant loses immense amounts of capital through evaporating cyanide, while simultaneously risking lethal environmental contamination. Moving to the physical reality of the ore brings up an absolute geometric rule. Reactants cannot dissolve what they cannot physically touch. This introduces grinding fineness as the primary physical imperative for the entire circuit. The ore must be crushed to a size that liberates the gold particles. There is no standard universal size for this. The required fineness depends entirely on the unique geological characteristics and the physical geometry of the gold locked within that specific deposit. This graph charts mineral processing test data, mapping gold leaching rates on the y-axis against the percentage of ore ground down to negative 0.074 millimeters on the x-axis. The baseline data reveals a clear limitation. When the ore is milled so that 70% of it passes through a 0.074 millimeter mesh, the leaching rate stalls out between 82 and 85%. But by increasing the one-stage grinding fineness so that 85% of the ore passes that same mesh size, the gold leaching rate spikes to an optimized 91%. Mechanical grinding establishes the geometric ceiling for the entire operation. If the gold remains trapped inside the rock matrix, chemical optimization is entirely useless. Once the particles are liberated, we move from individual grains of rock up to the bulk fluid dynamics of the processing tanks. Here we define our fifth operational variable, pulp density. This is the critical solid-to-liquid ratio of the slurry moving through the plant. High pulp density creates an immediate bottleneck. A dense, thick slurry severely restricts the diffusion rate of the chemical components, drastically slowing down the leaching speed because the reactants struggle to maneuver through the packed particles. Conversely, a low-density pulp maximizes that leaching speed, giving the reactants plenty of fluid to move through. But doing this exponentially increases the required volume of the processing equipment. Pumping massive amounts of water to lower the density requires a proportionally larger amount of cyanide agent to maintain the necessary concentration, driving up both upfront capital investment and daily operational costs. This brings us to the final variable that bounds the entire operation, the rigid limit of time. Cyanidation is an inherently slow kinetic process. Standard operations require a leaching time exceeding 24 hours. This asymptotic curve plots leaching time against recovery rate to illustrate a harsh kinetic reality. The reaction does not scale infinitely. It eventually hits a strict mathematical limit where extending time yields zero additional recovery. Consider test data from a low-grade oxidized gold ore containing carbon and arsenic. The parameters were heavily optimized, an incredibly fine 95% passing grind, a 33% pulp density, and a pH of 12. When researchers measured the extraction at 24 hours, 36 hours, and 48 hours, the leaching rate was completely static. It flatlined exactly at 81.48%. Leaving it in the tank for an extra day did absolutely nothing. Blindly altering physical density or extending processing time cannot force a higher recovery. Without precise data, these actions only waste space, time, and capital. When you pull back and view the entire cyanidation circuit, it operates as a single, highly calibrated system. The job of the metallurgist is to constantly balance the physical mass transfer limits of grinding fineness and pulp density against the strict chemical kinetic requirements of dissolved oxygen and cyanide dosage, all while keeping pH and temperature perfectly rigid to prevent lethal volatilization, and capping leaching times the exact moment the process hits the curve of diminishing returns. Because mineral characteristics vary wildly from deposit to deposit, attempting to guess standard operating parameters for these 6 factors is economically fatal. Mineral owners and process engineers must entrust qualified institutions to conduct rigorous processing tests on their specific ore before the plant is built. By mapping these 6 factors through empirical data rather than assumptions, metallurgists secure absolute process control, transforming a hazardous chemical reaction into a highly optimized, predictable economic engine.